Magnetic field of a solenoid using Ampere's circuital law. Magnetic field of a solenoid. Detailed derivation. A solenoid is a long cylindrical coil containing many closely wound turns carrying current I. Inside a long solenoid, the magnetic field is nearly uniform and parallel to the axis. To derive the magnetic field inside a long solenoid carrying current I. Given, length of solenoid equals L, radius equals R, number of turns equals N, current equals I. The number of turns per unit length, turn density, is N equals NL. Step 1, apply Ampere's circuital law. Ampere's law states, where B equals magnetic field, dl equals small element of path, IN equals current enclosed by the loop, mu0 equals permeability of free space. Step 2, choose an Amperian loop. Take a rectangular loop of as shown in the figure. Inside the solenoid, side of magnetic field is uniform. Band dl parallel. Therefore, integrating over length L, BDL equals BDL. BDL equals BL outside the solenoid, side CD, for a long solenoid, B0. Hence, contribution from side these 0. Vertical sides, AD and BC, here, magnetic field is perpendicular to DL. Since BDL equals BDL cos 90 equals 0, their contributions are also 0. Therefore, only side AB contributes, BDL equals BL. Step 3, find enclosed current. If there are N turns per unit length, then number of turns enclosed in lengthless NL. Each turn carries current I. Hence enclosed current is IN equals NL, I or IN equals nil. Step 4, substitute into Ampere's law. From Ampere's law, substituting gives dividing both sides by L. Since we obtain BL equals mu0 IN equals nil, BL equals mu0, nil, N equals NL, B equals mu0 NL. Meaning of symbol meaning B. Magnetic field inside solenoid I. Current through the solenoid N. Total number of turns L. Length of solenoid N equals N/L turns per unit length. Symbol meaning mu0. Permeability of free space, 4 pi times 10^7 tm/A. Y is magnetic field outside. Nearly 0. Outside the solenoid, magnetic fields due to neighboring turns are opposite in direction and nearly cancel each other. Therefore, outside 0. Physical significance. 1. Uniform magnetic field exists inside a long solenoid. 2. The field strength is directly proportional to current I. 3. The field strength increases with turn density. And 4. It does not depend on the radius of the solenoid. 5. A solenoid behaves like a bar magnet with north and south poles. 6. Used in electromagnets, relays, transformers, MRI machines, and inductors. Final result: B equals mu0 NLI. Inside a long solenoid, strong, uniform magnetic field. Outside a long solenoid, nearly 0 magnetic field. Step 1. Magnetic field due to one circular loop. Consider a single circular loop of radius r. The magnetic field at a point P O and its axis at a distance size dB equals mu20 IR2, where mu0 equals 4 pi times 10^7 tma1 I equals current through the loop. Step 2. Consider a small element of the solenoid. Take a thin section of thickness dx. Since there are N turns per unit length, dn equals n dx. This small section behaves like dn circular loops. Therefore, the field due to this element is dB equals mu20 IR2. Substituting dn equals n dx, dB equals mu20 R2. Step 3, integrate over the entire solenoid. If the solenoid extends from x equals 2L to x equals plus 2L, then total magnetic field is B equals dB. Therefore, using the standard integral hence, which becomes R2 plus dx x2, 3/2 equals R2 Rx2 plus x2. B equals mu0 2 R2 XL/2 R2 R2 plus x2L/2. B equals mu0 2 R2L plus L2 2. Step 4, long solenoid approximation. For a long solenoid, Lr. Hence, substituting R2 plus L2 2L2. B equals mu0 2 times LL/2. Therefore, since N equals NL, the magnetic field inside a long solenoid is B equals mu0 NLI. Magnetic field outside the solenoid. For a long solenoid, B0 because the magnetic fields produced by adjacent turns outside the coil largely cancel each other. Direction of magnetic field. Use the right hand grip rule, curl the fingers in the direction of current through the turns. The thumb points in the direction of the magnetic field inside the solenoid. Physical significance 1. Uniform magnetic field inside a long solenoid. Magnetic field lines are parallel and equally spaced, producing an almost constant magnetic field. 2. Depends on B. Hence, magnetic field increases with current I number of turns per unit length. And 3. Independent of radius. The field inside an ideal long solenoid does not depend on its radius. 4. Solenoid behaves like a bar magnet. One end acts as north pole. Other end acts as south pole. 5. Applications: electromagnets, transformers, electric bells, MRI machines, relays and inductors, particle accelerators. Final result: B equals mu0 NLI. Inside a long solenoid, uniform magnetic field. Outside a long solenoid, approximately zero magnetic field.
For beginners.